This is my video submission as part of the development project. The title of my project is Multi-Agent Self-Managing Town Simulation. This project has been made using Unreal Engine 4. The purpose of this project was to produce a simulation that modelled the behaviours of a town, with the aim of the simulation eventually being used to supplement larger games. The town is self-managing, sustainable in its growth, and based in the Middle Ages, and therefore focuses on the needs of a town from this era. However, it is designed to easily translate to different styles or time periods. To create the simulation, a multi-agent system was created using a number of existing algorithms and newly created ones that help to produce emergent intelligence. The details of these algorithms will be discussed throughout this demonstration. It is important to note that the interactions between the town created and any potential future applications have not been explored, but systems have been created that aim to introduce some of the impacts these systems may have. The menu provides a simple interface to control the simulation's graphics and control the testing of the simulation. Graphics settings allow for the simulation's performance to be tailored to the hardware. The testing menu provides control over the automatic testing, allowing the user to choose which variables are tested and whether testing is being carried out at all. This interface is mainly designed to support the development and demonstration of this project, rather than being required to satisfy the project's objectives. Before the simulation begins, a blank landscape is all that exists. The simulation populates the environment with a number of objects and creates the foundation of the town. The algorithm used to generate the environment is an adaptation of cellular automata, an evolutionary algorithm that evolves a bit field that represents the environment. Evolution occurs on a bit-by-bit basis using a rule set. This rule set determines the bit state based on the current bit state in relation to the state of the bits surrounding it. These bits are known as a neighborhood, and in this simulation, each neighborhood is of a 3x3 size. The effect of this generation can be seen here, creating clusters of trees in natural formations. Rocks and foraging bushes are not placed in formations, rather sporadically. This algorithm has a number of advantages. It allows for different environments to be generated that test the capabilities of the simulation, as well as providing a structure for mapping where all objects within the level are. This mapping can then be used to identify available locations for buildings to be placed. This algorithm was designed to work around an anchor point, in this case the town hall. The town hall is the central building to the simulation, acting as a site for depositing resources as well as the location for new agents to be created. All buildings are placed relative to this central town hall in the closest available building location. This menu here is the debug menu for task objects and shows the unique identifier for each object, what type of task it represents, as well as how much of its resource are left. All task resources are consumable. After they have been consumed, they are removed and the bit field is updated to reflect that the cell that they previously were in is now empty. This allows for the town to form more cohesive and optimal structures over time as the environment clears. Agents within the simulation appear to make realistic and informed decisions, choosing to perform the task that requires their attention. A lot of development time was spent creating a solution to this problem. The implementation uses a directed acyclic graph, a graph with one direction of flow where each node has a number of dependencies that must be met before it can be completed. This multi-tiered graph represents the relationship between resources. An example of this is one of the base resources is wood. Carpentry needs a certain amount of wood in order to produce timber. A house requires timber, and so on. Consideration of dependencies is fundamental in modeling the town's ecosystem, and the directed acyclic graph provided this. The graph has a topology. This is a linear ordering of nodes such that all connections to the node are used prior to visiting it. Traditionally, this would be static, but in this case an algorithm was created to dynamically maintain the graph topology. In order to do this, a priority equation was created to assign a priority to each task. This priority is then used to organize the order in which tasks should be completed. A lot of development time was spent creating this priority equation. The simulation is designed to appear intelligent and realistic. In order to achieve this, it had to balance efficiency with sustainability. The resultant algorithm created and the equation used to calculate the priorities results in a simulation that not only efficiently allocates tasks, considering the benefits of surplus resources, but also knows the dangers of unsustainable growth and avoids them. Agents have the capacity to navigate the environment realistically. They do this using an adaptation of an algorithm known as reciprocal collision avoidance. When a collision could occur, the algorithm calculates two sets of velocities. The first set represents velocities that could result in a collision. The second represents velocities that will not result in a collision. The algorithm assigns one agent a velocity from the first set and the other a velocity from the second set. The result is a seemingly natural interaction that guarantees that a collision is avoided without deviating too much from their previous path. The engine provided the main implementation of this algorithm, but time was spent optimizing the variables of this algorithm to perfect these interactions. The version of the algorithm used is known as the crowd avoidance algorithm. It is designed to work with the underlying navigation systems within Unreal, so it was perfect for this simulation. The simulation has a simple day-night cycle, with the time being shown in the top right corner, as well as based on the sun's position in the sky. This cycle directly relates to the schedule that the agents work on. During the day, they are active, completing tasks in order to grow the town. During the night, they are dormant, returning to the houses located throughout the town, and remaining there until morning. This system could be extended further to include further states that would add to the perceived realism of the simulation. The task assignment algorithm created allows agents to complete tasks to achieve an overarching goal. Within this simulation, the overarching goal is to grow. To grow, you require a certain amount of buildings and a certain amount of agents. This amount defines the limits of the simulation, which allows for controlled growth. The town can be seen here after it has developed. The buildings have been placed cohesively around the town hall. Testing drove development. This automatic graph directly indicates how successful the task assignment algorithm is, providing instant feedback as to how changes to this algorithm have impacted the simulation. The patterns produced by this graph can be used to determine behavior. It was identified that steady peaks relate to sustainability, and regular changes indicate oversaturation of tasks and an inability to manage itself sustainably. This enabled development to achieve a balance between efficiency and sustainability. A system that is overly efficient results in agents being reassigned regularly, whereas a simulation that focuses too much on sustainability won't grow quick enough. As previously mentioned, some of the impacts of games have been explored through other systems. In this case, there is a menu that allows for the recoverability of the simulation to be tested by reducing one of the resources or any of the resources to zero. This tests the simulation's ability to identify this deficit and reassign agents to best recover from this impact. This impact relates to the sort of impacts that may be introduced by a player, say destroying a town's resources. This simulation achieves the desired effect, satisfying all outlined objectives. The discussion here explains some of the details of implementation that led to this outcome, however more details can be found in my dissertation. Thank you for listening to my demonstration.